So we're continuing the discussion of acid-base equilibrium, which we've started already in chapter 14. Okay, so now we're in chapter 15. All right. Oh, let me get my hard copy going here. Okay, just checking a couple of things. Yep. All right. So think back to Le Chatelier's principle. And how do we change an equilibrium? Well, in this case, we're talking about changing an equilibrium by changing the concentration of a reactant or a product. One way is to directly either add or subtract reactant or product. Right? Just a direct attack on changing those values at equilibrium. The other is an indirect method, and I call it reaction coupling. We couple another reaction to the primary reaction, which allows us to either add a reactant or product or subtract. Most often we use it to subtract a reactant or a product simply because it's easy to add, but it's difficult to subtract from a reaction. So if we couple a second reaction to it, then we can influence the concentration of reactant or product with the second reaction, and that will produce a shift in the equilibrium of our principal reaction. And we do that by using this concept, the common ion effect. Okay, I need a new marker. Common ion effect. So when you have a reaction that's at equilibrium, say A plus B yields C plus D. And say, oops, D. Say you want to influence this reaction that's now at equilibrium by subtracting B. You want to remove B. Well, you need a reaction down here that includes B in it. That's the common ion. This secondary reaction must include the ion of interest, and it must be in such a way, say we have, we take this B, well, actually it might be a different coefficient for this one, plus, let's make up another one, say Z. And this one has an equilibrium that's way far to the right, the way we've written it. So we would produce, say, a BZ, okay? And say this is a solid. That means it would drop out of solution and no longer be available. So we put a certain amount of Z in this mixture, and it reacts with this B and removes it and decreases that amount. Which way is the reaction going to shift now? That way. That's using the common ion effect to influence the equilibrium. Now, that statement says influencing equilibrium by adding a common ion, but it doesn't have to be that way. We can subtract the common ion by this reaction. right? That's Le Chatelier's principle. So say we have hydrocyanic acid dissolved in water and it makes this acidic solution. What would happen if we added sodium cyanide to this reaction? Now, in this case, we are adding something. And this is not necessarily a coupling reaction, but we do. Let's get that reaction out here. If we have this reaction at equilibrium, right? Let's see. 3O plus CN minus. All right. If we have that scenario, and these are all soluble, then if we add sodium cyanide, what's the common ion? Right? Sodium cyanide is going to be completely soluble and produce those two ions. Sodium is a spectator. It's not a common ion for this reaction. Cyanide is common here. So by adding cyanide, we're going to shift the reaction back to the left. That's another example of the common ion effect. And what will that do to the acidity of the solution? Well, if we add more of this, Le Chatelier says we're going to consume some of that in order to go back this way. So we're going to reduce the hydronium concentration. That will increase the pH. It will reduce the amount of hydrogen ions in this form, and it will decrease the acidity or increase the pH. Okay. Now, we introduced that concept so that we can talk about buffers. Buffers take advantage of the common ion effect. By definition, a pH buffer or an acid-base buffer, because there are many types of buffers, but we're focusing on an acid-base buffer. It's simply a buffered solution resists a change in pH. It doesn't fix it. I mean, it's not like a reaction constant. It doesn't fix it at a position, but it does resist the change. In other words, if we have a buffered solution and we add some strong acid to it, the pH is not going to go wildly acidic. It's only going to decrease pH a small amount. Usually, not always, but usually, buffers are composed of the conjugate base of a weak acid, balanced with a certain amount of the undissociated acid. So if we had a weak acid here, right, that's weak, and we put it in solution, let's say, react with water and produces a hydronium ion plus A minus. This is the conjugate base. Okay? The buffered solution most often has some of this and some of that in solution together. And as it turns out, the ideal buffered solution for this one would be equal amounts. And I'll prove it to you in just a few minutes. This is the ideal buffered solution for this weak acid and its conjugate base. So what does that do? Why does that make it a buffered solution? Well, if this is a weak acid, it produces a strong conjugate base. All right? That being the case, there's always some of this and always some of that. Okay. Acetic acid, the acetate ion would be a good possibility. Let's hold that thought. Right. I'm gonna come back to that thought, that last point, in just a minute. What I want to emphasize now is what happens when you add an acid to this solution. Okay? What happens when you add an acid? Let's say a strong acid like hydrochloric acid. It's going to completely dissociate in those two ions. Now, which one's the common ion? Well, if we had written it correctly, it would be like this. Right there. We're adding hydronium ions to this solution. It's common with this side of the reaction. We're increasing the amount of hydronium, and it reacts with the strong base to drive the reaction back to the left. So what does that do for the pH? Well, we added some of this, right? So we would expect the pH to go up, but a large portion of it is being consumed by the reverse reaction. So the pH is moderated by this part of the reaction going backwards. That says when we add acid, the pH only slightly decreases. Then what if we add base? Well, if we add base, let's say we add sodium hydroxide. That dissociates into sodium plus hydroxyl ions. Okay. All right. So this is more not such a common ion effect as a coupled reaction. So what we have here is hydroxyls. Right? Where are the available protons? Where are the available hydrogen ions? They're right here. So this is, you can view hydroxyl as derived from water. Water has a Kw of 10 to the minus 14. So this is an extremely strong base. Very strong. And the most available protons for it to take are right here. So you add those together and you get, actually, you get two waters. So what does that do to the reaction? Well, we add the base and we expect the pH to go up because we're adding hydroxyls. But if it reacts with this and consumes those hydroxyls, not all of them, but most of them, it drives the reaction back this way because we have available weak acid to react with more water and produce more hydroniums. So that moderates the pH when we add a base. So the pH will increase slightly, but not a lot. That's the buffer effect. Whether you add acid or base, in this scenario, you get a shift in the equilibrium, according to Le Chatelier, to compensate for the stress that you've placed on the system. Now to that last point. When you add a strong acid or a base to a buffered solution, do the stoichiometry first. In other words, what that means is allow all of the added base or all of the added acid to completely react and see what would be the consequences. Then take those new values and apply them to your equilibrium, your buffer equation, to find out what the pH actually is. Okay, we'll do an example. All right, this is just the author's idea of an explanation for what happens when you add acid or base. Oh, and do the calculations also. All right. We mentioned this already. We mentioned this already. Okay. What we need now to gain a better understanding and a more useful calculating technique for buffered solutions is the Henderson-Hasselbalch equation. And I'm going to derive this right here on the board. Pay close attention, because you may see this question later and you need to be able to derive this equation. All right, Henderson and Hasselbalch were two separate scientists. Henderson came along first with his proposition, and Hasselbalch modified Henderson's equation with a newly developed concept called the pH. Okay, so what did Henderson do first? Henderson took this equation in its simplified version, right? His acid produced hydrogen ions plus the conjugate base, right? We're not using hydroniums here because it's simpler to do it this way. So the equilibrium expression for this acid would be what? Ka equals, let's use a small a, I think that's better. Ka equals concentration of hydrogen ions divided by the conjugate base, times the conjugate base, divided by that. Okay, that's our equilibrium expression. Let's see, did I put that in there? There we go. Okay. Henderson was interested in that value. So he just solved the equation for this hydrogen ion. Because at that time, when he was working, everybody understood that acidity of a solution was based upon the hydrogen ion concentration. So we solve it for hydrogen ions, and now we get, let's see, Ka times Ha over A minus. Okay? So what that told him was that Ka, being a constant at any given temperature, couldn't be fiddled with. But we could change these two concentrations. And if we change these ratios, then we could change the outcome of the hydrogen ion concentration. All right? So he simply solved it for that, and that's the Henderson equation. Well, in the meantime, after Henderson published this work, Sorensen came along and proposed his mathematical transformation of hydrogen ions to pH. So Hasselbalch took that equation and applied Sorensen's transformation, his modification, and he just said, I'm going to take the negative log of the entire equation. So what do we get? Negative log of hydrogen ions is pH. Okay? Negative log of Ka is pKa. So what do we have left over? What we have left over is the negative log of Ha over A minus. Now, why didn't Hasselbalch go ahead and say negative log of Ha is PHA, and this will be quotient, means this will be minus, so this will be minus the P A minus. Well, Hasselbalch realized that leaving it like this was more useful, because when we create a solution, the ratio of these two is the important factor. So he left it just like that, except for one more transition. Scientists don't like negatives. Negatives can get lost in calculations very easily. So whenever possible, we want to change them to positives when we can. So according to logarithms, the negative log of A divided by B is equal to the positive log of B divided by A. Right? That's a logarithmic identity. So all we have to do now to get rid of that positive, get that negative, is take the negative of that one and reverse these positions. And that is the Henderson-Hasselbalch equation. Okay, this is the timeline. Henderson worked in 1908. Sorensen proposed the pH system in 1909. And then Hasselbalch came along a few years later and used Sorensen's system to transform. There we go. To transform Henderson's equation into the combination. And that's the final equation. Now, can you derive that? Go through those steps? You should be able to. What does that tell us? That tells us that if you know the pKa for the weak acid that's used to make the buffer, then the pH of that buffer will be equal to the pKa when this term right here drops to 0. When does that happen? That happens when this concentration is equal to that concentration. If that's equal to that, then you've got the log of 1, and the log of 1 is 0. That's why earlier I said the ideal buffer pH for any acid is when the conjugate base and the undissociated acid concentrations are exactly equal. All right. That also means that it's the ratio that's important for producing the pH. If we had a 1 molar here and a 1 molar here, that would produce 1, give us the pH. If we had 0.01 molar and 0.01 molar, you get the same pH. Okay? That's analogous to the intensive property. Right? Concentrations don't matter because we've ratioed them. But if you have a situation where you want a buffer that will maintain a narrow range of pH, when you add large amounts of acid or base, then this one is better. It has a higher buffer capacity. Right? That's an extensive property. Buffer capacity will be increased here. It'd be the same pH to start with, but this capacity is much larger than that one. Okay. So we take the Henderson-Hasselbalch equation. I'll leave it here like that and work around it. If we have a buffer that's composed of 0.45 molar acetic acid, which is this one right here, okay. 0.45 molar is that one, and 0.85 molar sodium acetate, which means what? Well, sodium acetate is completely soluble. If you have 0.85 molar of the salt, you're going to have 0.85 molar of the acetate ion. All right? So we have this part of the equation done. The Ka for acetic acid is 1.8 times 10 to the minus 5. What's the pKa? The negative log of that value. So I just put in 1.8, 10 to the minus 5. Take the log and change the sign. 4.74. Let's see. Yeah, 4.74. So this is 4.74. And that's equal to the pH. So let's see. I think I've got it animated there. Well, yeah. Let's see if I get the same number. 0.85 divided by 0.45 and then plus. Yep, plus. Oops, what did I do wrong? Hold on a second. Let's do the pKa again. Negative log of 1.8 exponent minus 5 log negative 4.74. Okay. Oh, 0.85 enter 0.45 divide, take the log of that. Okay, that's 0.28. 0.28. Added to 475 is 502. 5.02 pH. Okay. This is so much easier than drawing out an ice table. If we know these to be the equilibrium concentrations of the conjugate base and the undissociated acid, or the unionized acid, I should say, then it's a simple matter of a calculation to determine what's the pH of the solution. Now, sometimes you do have to use the ice table, but when you know both the Ka or the pKa of the acid and the concentrations of the acid and the conjugate base, this calculation works fine. All right. We talked about this already. What happens when you add an acid or a base to the solution? All right. Okay, buffers contain relatively large concentrations of the weak acid and its conjugate base. That's if we want a very high buffer capacity. Doesn't have to be a large amounts, but other factors in your experimentation may dictate what concentration is acceptable. If you have a buffer that you're using for living systems, then you don't want a huge ionic strength in that solution because it will damage the cells. So a lower concentration will give you the right pH, but will not damage the cells. That's one possible scenario. So the added hydrogen ions react with the strong conjugate base. We showed that earlier. Not there anymore. In order to moderate the pH. And the hydroxyls react with the weak acid. Now I showed you one way where it reacted actually with the hydronium ion, with the hydroxyl, with the hydrogen ions. But we could just as easily write it in terms of the hydroxyls reacting with the undissociated acid. Right? And that would give us more A minus and water. So this would favor the product side of our reaction as written. Okay. Yeah, that is true. The actual pH in the buffered solution is determined by the two variables and the ratio of these two variables, the conjugate base to the acid. Buffer capacity is another concept, and I'm just giving you this for illustration purposes. You're not going to have to do calculations with these, but the buffer capacity is defined as the amount of protons or hydroxide ions that the buffer can absorb without significant change in pH. And that's determined by the magnitude of these two concentrations. So if you want a buffer with large capacity, make sure those concentrations are large. And in non-living systems, then you can go relatively high with the concentrations. Other factors may enter eventually, but living systems are more sensitive to high concentrations of these components. So you have to be more careful with those. Okay, optimal buffering occurs when the acid and the conjugate base are equal in concentration. And I'm going to show you something in just a minute that is going to be useful to you for one of your labs, upcoming labs. In fact, we've got Le Chatelier's lab coming up next week, and the one after that is Ka of acetic acid. And I'm going to show you something about that in a minute. So here's how we quantify. Buffering capacity is given as beta is equal to the change in the change in number, the normality. That's what N equals. We talked about acids and bases. I don't think we have covered that yet. Normality. Hold on. I thought we had covered normality before. Normality refers to the concentration of either hydrogen ions or hydroxyl ions. And it's independent. Well, it's usefully, practically independent of where they came from. So 1 molar HCl is equal to 1 normal HCl, simply because molarity says moles of this molecule per liter. This is normal, which is one equivalent of HCl. An equivalent is based upon how many hydrogens are produced by each molecule. So if we have H2SO4, right, and we have a half molar, that is 1 normal H2SO4. Because for each molecule, you get 2 hydrogens. And for a half molar concentration of this molecule, you get a whole molar of hydrogen ions, which is an equivalent. So when we're talking about this, when we add so many normal, so many equivalents of acid or base, then it's going to produce a certain change in pH. So we ratio the amount of acid or base added to the change in its pH, and the value will vary depending on the buffering solution. And it will be much, much higher, much greater if you can add a lot of this and get a small amount of that, right? It's like any quotient. If you can keep this really small, but you can make that large, then this capacity value increases significantly. Okay, that's just an explanation. For example, right, 0.85 equivalents of acid per unit of pH. All right. So let's move on. The pKa of a weak acid to be used in the buffer should be as close as possible to the desired pH. Now we're going to explain that on the next page. We're going to do it with a titration curve. I have to explain what titration is. And there's a more complete discussion that comes with the lab where we determine the Ka of acetic acid. But the titration curve plots in our case added base, and we say hydroxide ions. So how much have you added from the beginning to whenever? And then the response, the dependent variable is pH. How does the pH change? So if we're starting with an acid, we would add base. If we're starting with a base, we would add acid, right? It works both ways, but I'm going to use this illustration for, say we have a pH here that starts down low, and as you add base, the pH starts to increase. Notice that when you begin with a weak acid, it's mostly that, right? You don't have any conjugate base yet. But as you add hydroxyls, you start to build up. You start to build up the conjugate base, right? And it consumes these hydroxyls. You don't get the significant movement that way until you start to get enough of them. So the pH increases kind of steeply at first, but then it flattens out in here. In this region, you've built up enough of this so that as you add hydroxyls, you get the Le Chatelier's principle takes effect. And you stabilize the pH in this region. This is the buffer zone. Right in here. Now, once you've added enough base where you exhausted the acid, the pH starts to rise precipitously now, like that, until it gets to some point and it levels off. So at this point right here in the middle of that steep part, this is the equivalence. The equivalence point. And the equivalence point is where the concentration of the original acid equals the concentration of added base. Right? That's the equivalence point. And for some titrations, that's what you want. You want to know how much acid is in there. So you use a base of known concentration, and you can determine how much acid is in the solution. But for our purposes, we want to know at what point is this true? When do we have this equal to that? Well, if you look at it in these terms, where you've got this concentration and that concentration, where do you have equal amounts? When half of this has been used up, now it's over here, right? If you use up half of that, now it's over here, and you have what's left here is equal to what's new there. So where do you have this? At half equivalence. This is 1/2 equivalence. So that point right there is where this concentration equals this concentration. And what did we say from Henderson-Hasselbalch? When these two are equal, this term drops out. And now pH is equal to pKa. So if you're at this point on your graph and you follow this line over here, that is pKa. And this is the ideal for any buffer if the pK is equal to your pH of the buffer. That's right in the middle of the buffer zone. All right, I think I got a graph coming up. That's explanations I just gave you on the board. So there's a plot. In fact, this is acetic acid. So acetic acid starts off in about 2.5 pH, and eventually we get to the mid to high 4 pH right in here. Like, I don't know, 4.6 or 7, something like that. That would be the pKa. Now, how do you calculate the Ka from the pKa? Easy. If pKa is equal to the negative log of the Ka, then all you have to do is say 10 to the minus pKa. And that's equal to Ka. So we're going to do one of these in the lab. Not this coming lab, but the one after it. Lab number 4, I believe. Learn how to titrate. Actually, we've already done titration in CHEM103. 104, we're going to use the same setup, but we're going to check the pH as we add base so that we can get this plot. We get pH versus added base. Then we can get this plot, and that allows us to deduce the pKa for this reaction. Okay. There we go. All right. So if we titrate sodium hydroxide with HNO3, are we going to get a valid buffer zone? That's a little misleading. It's really steep down in this region, right? It doesn't produce a good buffer. Strong acid, strong base will not produce a good buffer. In this case, we're going backwards. We're adding acid to base, and we can get an equivalence point. That's always possible, but we don't get a good buffer. Okay. Weak acid with a strong base titration. This is the methodology that we're going to be using. And we'll come back on Tuesday and use the review documents for Chapter 14, which is a separate one. Chapter 15 is a separate document. I'll have those combined so we can talk about all of them at the same time and work some more of these problems. When we say a two-step problem for titration, where we do stoichiometry first, we essentially run the reaction to completion with the values that were given. The acid and the base, we react them so that usually all of one of them is consumed. And then we say what's left over, and then we attack that one from the equilibrium side. Okay, here's an example. I hope we're going to do this one. This may just be a preliminary. If we have 0.1 mole of hydrogen cyanide with 0.04 moles of sodium hydroxide in 1 liter of aqueous solution, we put those together. Ask yourself, what's the major species? If you have hydrogen cyanide in solution, it's not going to be dissociated because its Ka is 10 to the minus 10. So this is a major, that's the major species. The other major species are sodium and hydroxide because they're completely soluble. And then, of course, water. Okay. That's before any reaction takes place. Okay. So there's possibilities, right, for the water and the hydrogen cyanide ionization. Then we can also get hydrogen cyanide and hydroxyls reacting to produce cyanide ions plus water. And then we've got sodium dissociation and sodium reacting with water, which it doesn't do. So we throw those two out and we look at which one controls the pH. Well, what we need is to conduct the reaction and then say, now what are the species after the reaction? Let's go back. So what are we going to get? Well, we could get some dissociation, but not much. And water, not much. So the major reaction at first is going to be hydrogen cyanide plus hydroxyls to produce cyanide ions that can react. So that's where we're at. That's what this reaction tells us. So when the reaction takes place, we may still have some hydrogen cyanide. We have some cyanide ions. We have water and sodium. If we react all of the hydroxide with hydrogen cyanide. Now, the question is, do we have enough acid to completely consume all of the hydroxide? Let's go back. Let's see what the concentrations were. Okay, 0.1 molar HCN, 0.04 molar sodium hydroxide. Yes, all of the hydroxide will be consumed because it's a one-to-one relationship and we have less of sodium hydroxide. So that's a good assumption from this slide right here. All of the hydroxide is consumed. It's no longer there. Okay, so this is as far as we're going to take this problem. What we would do from here is we would say, okay, that would be the stoichiometry part of the problem. We reacted all of the hydroxide with the available hydrocyanic acid. And what do we have left? We have some hydrocyanic left behind. We have some cyanide ion there. And then we can apply either the ice table or the Henderson-Hasselbalch equation for the equilibrium. So now we're going to shift to we're going to shift to acetic acid and apply the same concepts. All right, so what are we reacting? Sodium hydroxide again? Okay, so we're going to have that. Before the reaction starts, we're going to have this sodium hydroxide and water. Major species, okay? So what reactions are valid? Those are not valid. So the reaction that we want first is the third one. We're going to consume all of the hydroxide, I think. Let's go back and see. Let's see, 0.2 moles of H2 of the acetic acid, 0.03 sodium hydroxide. Yes, we're going to consume all of the sodium hydroxide. Okay, there we go. So we know what the K values are. We know that the dominant reaction, the stoichiometry, is going to be the one with the that consumes all of the hydroxide. Okay. The strongest proton donor is going to be acetic acid, right, because it has a higher Ka than water. So when it does that, what do we have left over afterwards? Okay. What we have left over is we have some, well, this is the stoichiometry part, excuse me. This is a stoichiometry. 0.2 Yeah, that should be labeled as let the reaction go to completion. This is the stoichiometry. We initially have 0.2 molar acetic acid and 0.03 molar hydroxide. So we're going to consume all of the hydroxide. That's why it goes to 0 here. And these are the starting values for the equilibrium. So now we need to write the equilibrium equation where we have some acetic acid left, right, from the previous 1.17 molar. And we essentially have very little hydroniums. And we have 0.03 of the conjugate base. Now, which way is the reaction going? Well, since we have very little acid in there, the hydronium ions, the reaction is going to move to the right, which gives us positive X on the right-hand side, a negative X on the left. So our equilibrium is 0.17 minus X for the acetic acid. Hydronium is going to produce some, and that's going to give us our pH, that X value. And then the conjugate base is 0.030 plus X. Okay, so if we take the Ka and set it equal to our equation, and we assume that X is going to be very small because the Ka for acetic acid is very small, then we get an X hydrogen ion concentration and calculate 3.99 is the pH, right? And that's an ice table. So we did stoichiometry first, then we did equilibrium second. Now what I want to do is take the equilibrium concentrations. After the stoichiometry is done, now we have 0.03 molar in the numerator of the Henderson-Hasselbalch equation and 0.17 molar in the denominator. And we know that the pKa is the negative log of the Ka for acetic acid. That's 4.74. Calculate pH is 3.99. Exactly the same as the hard way. Okay. So what if we do a different titration with acetic acid, and we say we want to know the pH of a 100 ml solution of 0.1 molar acetic acid, which has a Ka value of 1.8 times 10 to the minus 5. Right? Do we need all that information? No, we don't. We don't need all of it. We don't need a 100 milliliter solution because we already have the concentrations. So we're starting off with 0.1 molar and no hydrogen ions and no conjugate base. And then we run our equilibrium, our ice table, and determine that the pH is 2.87. So what if we have, that's where we just have pure acetic acid. So what that tells me is, in that titration curve, our starting pH, if it was 0.1 molar acetic acid, would be 2.87. The pH may vary depending on the concentration because this is just the acid. But if we titrate that with sodium hydroxide, say we have a solution by mixing now we do need to know the volume, 100 milliliters of 0.1 molar acetic acid and 50 milliliters of 0.1 molar sodium hydroxide. Now what's the pH? Right. We're going to change the concentration because we changed the volume. We went from 100 milliliters to 150 milliliters of our final solution. So we want to go to completion for the reaction. And we calculate the initial concentration. Once we add all that together, we get, right, how do you calculate the concentration of acetic acid initially? It's 0.1 molar, 0.1 molar acetic acid times 100 milliliters. That's the moles of acetic acid divided by 150 milliliters. And that's 0.0667 molar. And I put another 6 in there. No, that's it. That's how we got the initial concentration for the stoichiometry of this reaction, because we changed the volume and then we reacted. We can do the same thing with the hydroxyls. We say 0.1 molar sodium hydroxide times 50 milliliters divided by 150, which gives us 0.0333 molar. Okay. Now, we're going to use up all the hydroxide and some of the acid and produce some conjugate base. This is the stoichiometry part. Now we take those values and put them in the Henderson-Hasselbalch equation, and we find that the pH, right, the equilibrium concentration for acetic acid is 0.0334, and for the conjugate base is 0.0333. So we essentially have a one-to-one relationship, and the pH is equal to the pKa. 4.74 will be the pH of this solution. All right. One more. This time, remember I mentioned most buffers are made of weak acid and its conjugate base. In this case, we've got a weak base and its conjugate acid. Okay, so we want to calculate the pH of a solution made by mixing 100 milliliters of a 0.1 molar solution of ammonia, and that has a Kb of 1.8 times 10 to the minus 5, and 50 milliliters of 0.1 molar ammonium chloride. Okay, so there's the reaction. We need to recalculate the concentration of ammonia before the reaction occurs. So we've got ammonia is 0.1 molar times 100 milliliters divided by 150. Again, that gives us 0.0667 molar ammonia. Do the same thing for ammonium before they react. Then when they react, we're going to produce some hydroxyl, which means we're also going to produce some more ammonium ion. That's why the plus X's are on the right-hand side. And we're going to lose some of that ammonia. So we set up our equilibrium. That's the stoichiometry. There we go. And that reaction requires that we use the Kb expression, right? Ammonium ion times hydroxyl ion divided by ammonia. And then we make an assumption that X is going to be very small. So we calculate the hydroxyl ion concentration, and we could calculate for the 5% rule, but in the interest of time, I didn't put that in here. It does satisfy the 5% rule. So we calculate the POH, subtract it from 14, and the pH is equal to 9.56. All right. What if we use the Henderson-Hasselbalch? Equilibrium approximation is 0.033 for ammonium and 0.0667 for the conjugate base. Right? It has to be acid versus conjugate base. So that means we have to write the reaction in terms of ammonium ion reacting with water to produce its conjugate base. And then, not only that, we have the Kb, we don't have the Ka. We have to calculate the Ka and the pKa for this reaction, 9.25. Now we can use Henderson-Hasselbalch. Put those values in, and we get 9.56, which should be the same as before. All right. All right, we could do this. Let's see, how much time is this going to take? We're already into our lab time. Calculate the pH of a solution made by mixing 1 liter of 0.5 molar ammonia with 0.5 liters of 0.1 molar ammonium chloride. And then you add 0.1 mole of HCl gas. Why do we bubble HCl gas through there? So that we don't change the volume. That's why. So the initial concentration of ammonia, the number of moles is 0.5, ammonium is 0.1. Now we need, okay. Sometimes when we're doing stoichiometry, it's more useful to use absolute amounts. That's what we're doing here, because we know how much ammonia is in there, 0.5 moles. And we know how much hydrogen ion we're adding to it, 0.1 mole as hydrogen chloride gas. And that's before reaction. And before reaction, we have 0.1 mole of ammonia. So now after reaction, we're going to consume all of that hydrogen ion by reacting it with ammonia and making ammonium. And after the reaction, we have 0.4 moles of ammonia and no hydrogen ions yet, and 0.2 moles of ammonium. Now we can convert it back to concentration if we know the final volume, right? We added 1 liter plus 0.5 liters, that's 1.5 liters. So we calculate 0.1 divided by 1.5. Excuse me. I looked at the wrong one. Oh, I did. Oh, it got chopped off. Yeah, it got chopped off at the bottom. No, it didn't. There it is, 0.4 moles. Excuse me. 0.4 moles of ammonia and 0.2 moles of ammonium divided by 1.5 liters. That gives us our new concentration of base and acid. Now we can use the Henderson-Hasselbalch equation. We need to be sure to use the Ka, and we put the conjugate base on top and the acid on the bottom, right? The acid is ammonium, and we get a pH of 9.55. So the Henderson-Hasselbalch here came to the rescue. We didn't have to use a full-blown ice table. All right. Now here's a question that chemists often ask themselves when they're going to do a titration. We want to know where is the equivalence point? If we have 100 milliliters of 0.1 molar acetic acid, and we titrate it with 0.1 molar sodium hydroxide solution, we want to know at what pH will the equivalence point be. Why? Because when you're titrating, I may have explained this before last semester. When you're titrating and you want to know that value, that's the pH at equivalence. We don't want to have to use pH or a pH meter for every titration. If you've got 100 or 200 of these things to do, you want something quicker. And that's where we use an indicator. So you want to use an indicator that changes color at the equivalence point, or very near the equivalence point. So if we know where the equivalence point is, we can choose our indicator, the best indicator that will change color at that pH. That's what this problem is all about. So, we know that the equivalence point is going to be that point at which the moles of acid equals the moles of base. In this case, we have a monoprotic acid and a monohydroxyl base, so we can use moles and we don't have to worry with equivalence. So the total volume is going to be 0.2 liters, right? If we have 0.1 molar acetic acid and 0.1 molar sodium hydroxide, then we're going to have equal volumes. Since they're the same concentration, we're going to reach our equivalence point at exactly equal volume. So that means if we have 100 milliliters of acetic acid, it's going to take 100 milliliters of base. So that means the final volume is 200 milliliters or 0.2 liters. Then we can calculate the concentration of both of them at 0.05 molar. So 0.05 molar then, with a change where both of them disappear, and we end up with 0.05 molar acetate ion. Okay, that's the stoichiometry. Now the dominant reaction is going to be 0.05 molar acetate ion plus water. And that's going to be our equilibrium expression. Right? This is going to be a Kb reaction. So we have to calculate Kb from the Ka of 1.8 times 10 to the minus 5 gives us 5.6 times 10 to the minus 2 Kb for this reaction. And if we set up the reaction as such and approximate the X since it's a very small value, and this is going to give us the OH, the hydroxyl concentration, calculate the POH, subtract it from 14, and you're going to reach equivalence at 8.72. Okay? For this situation, the equivalence is going to be at 8.72. Now, we can do that for any number of other acids, but this is to illustrate the fact that if you know the Ka, you know what the shape of the curve is going to look like. If the Ka is in the neighborhood of 10 to the minus 4 for acetic acid, you know that your equivalence is going to be somewhere around 8.5 or 8.72. But if you're using a weak acid with a larger Ka, your equivalence point is going to be at a lower pH. And consequently, if you have a higher Ka for your weak acid, the equivalence point is going to happen at a much higher pH. Okay? We can do the same thing for titrating a weak base with a strong acid. We can also titrate polyprotic acids like phosphoric acid. Remember, phosphoric acid, right? Phosphoric acid, when we titrate it with a base, let's see, we lose? No, we didn't. Okay, just made a noise. When we titrate it with a base, it's going to take, the first one is going to take PO4 minus plus water. That's the first K. This is the K. This is the first pKa 1. And then we keep adding base. And after we've consumed all this, we're going to add base and consume this one. And this will give us PO4 2 minus plus water. And this is a pKa 2 for the second proton. Let's see. Yeah. And then we have HPO4 2 minus. Keep adding base. And we get PO4 3 minus plus water. And this has a pKa that's completely different than the others. And the shape of the curve looks like what we see down there. The first midpoint is the pKa 1. The second midpoint is the pKa 2. The third midpoint is the pKa 3. So what does that mean? That means phosphoric acid can be buffered at 3 different pHs, equal to its individual pKa's. So it could be buffered at this one, or that one, or that one. And you'll find in biological buffers, where you're working with living systems, phosphoric acid is a good choice because you can get it buffered at low concentrations, and you can pick the buffer zone depending on the reaction or the environment that you want for your cell culture. Okay, so an indicator changes color at or near the equivalence point. So we have an end point is the change in color, and the equivalence point is the actual base equals acid equivalence. Okay. Phenolphthalein, here's an example. We have to think of, when you think of indicators, think of an indicator as a weak acid or a weak base. In this case, we're thinking of the phenolphthalein indicator as a weak acid. And we abbreviate like this as the indicator with its acidic hydrogen. And in the reaction, is set up in equilibrium like this with a K value, right? It has a K, let's say, let's do this, K indicator like that. Then we can have this expression over this expression for any indicator. And on one side, for phenolphthalein, this side is clear. And this side is pink. Okay? And we used phenolphthalein before. That means what? That means this side is the basic side. This is the conjugate base. This is the acid. So if it's on this side, that means we've got acid in solution that's driving the reaction back this way to keep it clear. But as we consume, as we add hydroxyls, right, and consume hydrogen ions, we're shifting that direction, and eventually you reach the point where you see pink instead of clear. And the Ka for this value is 3.98 times 10 to the minus 10. And the pKa is 9.4. So 9.4 pH is the center of the indicator's color range, color change. So that's why we use this one for the titration of acetic acid with sodium hydroxide, because this pH, this color change happens at very near the pH, 8.74, I think it was, very near the pH change for sodium hydroxide with acetic acid. And you don't have to remember those. That's just the change in structure that gives you the different color for the phenolphthalein molecule. All right. So here we have the conversion from the acid to the conjugate base for any indicator will give you a color change. Now, as a practical matter, we have to introduce, since we're looking at color changes, we have to introduce physiology. You know, under what circumstances will your eyes see a difference in color? Right? The difference in color occurs at a ratio of 10 to 1, roughly 10 to 1, difference in concentration. So the difference in concentration between these two over this one is approximately plus or minus 10, right? 10 to 1. So, I mean, that's a large gap. But since we're talking about pHs, what is the pH change here? If we talk about the pH versus the P indicator, that is a change of only 1 unit, plus or minus 1 unit. Plus or minus 1 unit around this value. So this change occurs between 8.4 and 10.4. That's why when we get to that endpoint we did last semester, we have to be very careful. We want to add just the smallest drop when we're close to the endpoint, the smallest drop possible. Because the physiological range is so wide. Now, this is easier to deal with, right? This chart, and it's kind of small for the slide, but what I'm seeing is we have these indicators down the left-hand side, and then we have the effective color change pH ranges in these bars. So if we look for phenolphthalein down here, oops, sorry, got to go back. There we go. We see that it's changing here around pH 9. Right. So if I had a reaction that was going to need a pH change, the equivalence is going to happen at, say, 6. I might use brome cresol purple, right? Because that 6 is right in the middle. Changes from yellow to dark red. There are also indicators that are combinations of the 2 or 3 or 4, right? Universal indicators have several of them, like 5 or 6 indicators together, and they'll change through a sequence of colors. Those are what you normally see on, see if I have some with me. Normally what you see on pH paper, right? So you'll go through a range, go through red for pH 1, then go up through orange, and then 7 will be yellow, and then you keep going and you go up through blue. These pH papers are impregnated with indicators, a number of different indicators to show changes, and you have to choose your indicators carefully because you don't want one to change into a color that's going to interfere with subsequent changes. Okay. So this is the last slide. And when you decide what your equivalence point is, then you can go to a chart like this and find the best indicator for doing multiple titrations without having to use a pH meter for every one. Okay, I think that's it.